Thank you for joining me this evening for a little journey into our planet. Here's our planet looking from the outside. We have a very, very long history looking up from our planet to the skies. And we have a very long history looking at our planet, at the geology, at the heterogeneity, at the evidence that there's dynamics on our planet. We have a fairly short history compared to anything in physics or astrophysics, of actually looking down into our planet, okay? It's roughly 150 years ago that we, for the first time, measured an earthquake from far away. And it's only in the past decades that we've tried to image what is happening inside our planet. And that's what I'll show you today. Here's an artist depiction, okay? This is a slightly exaggerated picture of there is dynamics happening in our planet. There are places on the planet where new plates form, and there are places on the planet where plates get destroyed, and then there's circulation from within, okay? But remember, the mantle is a solid, so things are moving, but they're moving on geological timescales, okay? So it never, it won't look as exciting as it is here. So, in my job, I look at wiggles. I basically look at these wiggles to listen to what is happening inside the planet. So here you can see a single seismogram, but obviously to understand our planet, we have to look at many different seismograms. And so we record our wiggles using seismometer. Here you can see a field deployment from one of our PhD students actually deploying seismometers on Iceland as the eruption is happening in the background, okay? And so here they're deploying the seismometers to track where the magma is moving underground and where the next eruption might occur, because all this magma movement comes with really small earthquakes. But here you roughly see the setup. It's best to dig a seismometer into the ground. Here there's a solar panel next to it to power it over time. This is a temporary setup, but all over the world we have seismometers that are kind of permanently measuring. The data gets shared via satellites. And we do extremely well in the field in sharing our seismic data. So I can just go online and download the data for a specific earthquake at seismometers all across the globe. Okay? This basically means we all have access to the same data. So if I do a study on something, somebody else should be able to download the same data and reproduce my science in the same way. We basically all share all of our experimental results. Seismometers really exploded roughly in the 1960s. Suddenly, there were seismometers everywhere. Anyone have an idea why? Yeah? Nuclear tests. So different countries were doing nuclear tests, and seismometers were the immediate way to detect the nuclear test, locate where it happened, and figure out how big it was, okay? And so, a lot of seismology has piggybacked off of that has expanded, and then become a good monitoring tool as well for earthquakes. So here you can see earthquakes happening every month across the globe. You can see it's starting to highlight the plate boundaries where these earthquakes tend to happen. And obviously a lot of seismology is focused on this earthquake seismology. We need to understand these earthquakes. We need to know how they happen. And ideally, we need to predict them, but we're nowhere near to predicting them, so we try to forecast them, right? So that is a lot of seismology. But I am what we call a structural seismologist, and so we're from a different flavor. We assume that we roughly understand these earthquakes, and then we can use the data from these earthquakes to look at what the waves have traveled through in between, and to learn about the structures in between, and therefore the dynamics of our planet. In the end, we try to understand what is driving the plates, what eventually is driving earthquakes, okay? It's a little bit circular. We use data from the earthquakes eventually to study why the earthquakes happen. Here's a computer simulation of an earthquake. So this is done by a supercomputer. So this is solving the wave equation on a global scale. The finer the detail of the structure that we want to model and the higher the frequency of the wave we want to model, the bigger the supercomputer we need to make these kind of simulations, right? Here, At this point, you're mainly seeing the surface waves that ripple out across the surface, and you can see they're sensitive to local structures and interactions, right? So you can see there's information in that wave field about the local structure, and that is what we try to do in Earth as well. So here's a different video. Now we're looking at a cross-section of an earthquake, and we're looking at the waves as they propagate into the Earth. Okay, so here's our earthquake, okay? And here is the wave fields propagating out. They interact with all sorts of boundaries, reflecting, refracting, etc. You can see that it quickly becomes reasonably complicated. Okay. So yeah, how can we pull apart this wave field? So the first distinction we make in seismology is for the surface waves that expand across the surface of our planet, and the body waves that expand in 3D through the body of our planet. And body waves we split into P and S waves. But P waves, we call P either primary because they're the first arriving, or P for pressure wave, but you will know these as longitudinal waves, okay? The direction of the displacement is in the direction of propagation, similar to sound waves in this room. And S waves, which we refer to as secondary or shear waves, you will know as transverse wave. Their displacement is orthogonal to the direction of propagation. All right, so yeah, just the lingo of our own subfield. So here's a little video of a compressional wave going through this medium, and you can see the little particles go back and forth as the pressure wave propagates across the medium. And in the bottom here, you can see the same for a shear wave or a transverse wave. Okay, so going back to this movie that you saw before, okay, so now, apologies. So same movie. So the yellow-red here is our compressional wave, propagating much faster. And the blue-green is our shear wave, going a little lower. And you see it's not going into the outer core, which is significant. And yeah, you can see all the complexities arising as the waves go through. And so, yeah, to try and make sense of this, we give a name to each wave or phase or little bit of energy and the kind of path that is taken through the Earth. So if my earthquake, let me use the pointer on here, hopefully see better and I point at all screens at the same time. If my earthquake is happening over here and I have a seismometer over here, then I have a P wave going in between and it has this path, right? It has this slightly curved path, right? That is because the velocity is increasing as a function of depth and my wave is refracting as it goes on the way, okay? That's Snell's law in action there. And then if I have a seismometer here on the other side of the Earth, I might denote it as a P for the best bit in the mantle. We denote a K for the path that it has within the core, and then it has another P path. And so this wave is called a PKP wave, okay? So we just keep adding letters for the different parts of the Earth that it might travel through. So if I have a wave that has gone all the way through the inner core and is observed on the other side of the planet, I would call it a PKIKP wave. If that wave reflects off of the surface there and goes all the way back through the planet and is observed at a seismometer here, I would call it a PKIKP wave. Okay? So yeah, you can continue playing that game, and people can, if the earthquake is big enough, you can see some quite exotic phases that have gone through these paths. Okay, so yeah, so that are the bottom waves. Now the surface waves, they tend to have more energy in them as is, and then they only spread out in 2D instead of in 3D in their energy, and that means trouble, okay? So the surface waves are the ones you need to worry about in an earthquake. They come in two flavors. There's a Rayleigh wave that has this circular retrograde particle motion as it goes across the surface. So it's sort of circular wave, okay? If in an earthquake they have an acceleration that is above g, they will throw you off the ground, right? And then you have these love waves, which shear the planet, and they are big trouble for buildings that are particularly hard to design against these shearing. Okay, so the surface waves play a big role in understanding seismic hazard. How do we expect them to be locally amplified by the structure or some sediment basin? What are building responses? What sort of resonance frequencies do buildings have? Don't have to worry about it too much here, but in certain countries you do. And you want to try to warn for them, okay? So the good news is that our P waves propagate much faster. And so countries are really trying to work on using that P wave as an earthquake early warning to warn for the later surface waves, okay? So, for example, Japan is really good at it. Their earthquakes happen out in ocean. So in the Tohoku 2011 earthquake, they had a really good warning system. It came up on people's TVs, phones, etc. And people got a warning, except in that case, they totally underestimated the tsunami, which was a disaster. Okay, so a little bit of a short history then about how we discovered these layers in our planet. I'll wait a minute for this group to join us. Okay, a little bit over a century ago, Richard Oldham was the first to discover an outer core, a sense of an outer core. And what he found was that there's regions on the Earth where there was no main compressional wave arriving, calling it a P shadow zone. His estimate of the core radius, though, was a little bit off. He had about 40% of the planet. Now, at least, well, who knows what the truth is, but now at least we think it's about 55% of our planet in radius, not in volume. And so this is what it looks like for a P wave pattern. As it enters the core, it refracts downwards. And so we get regions on the planet where we don't get direct P wave energy, and we call it a P wave shadow zone. For our S waves, this shadow zone is a lot bigger. And that is the big giveaway that our core is a liquid. It does not sustain shear or transverse wave that go through. And so that was later more evaluated what the size was, and actually that our core is a liquid. A couple decades later, Inge Lehmann, a Danish seismologist, she detected the inner core. And so she found a tiny, tiny wiggle in the seismogram that she tried to explain from a reflection off of the inner core. This is, she postulated or guessed that the inner core would be a solid, but it's only much later that we actually confirmed that the inner core is a solid again, okay? So while the inner core is getting hotter, the pressures there are just getting so high that the liquid becomes a solid again at the inner core. As our planet is cooling as a whole, right, our inner core is growing in size and solidifying, roughly 1 millimeter per year for inner core growth. She named her paper, she named this phase, which we now name differently P prime, and she named her scientific paper P prime, which that is the shortest title for a scientific paper. Anyway. Okay, so a little bit summary of our first order layered Earth. We have a mantle, which is a solid and a rock, but very hot. We have an outer core that is even hotter, but it's also made of a metal, iron, nickel mixture with some light elements, and it's a liquid, and it's moving very quickly. And then we have our inner core, which is a solid, okay? And we know the outer core is moving quickly because it sets us up with a magnetic field, which protects us from the solar radiation, right? So without our outer core, we wouldn't actually be able to live on this planet. It's one of the key features why Earth has and stores life. And we know about other planets like Venus and Mars that don't have a magnetic field. So what can we do further than this layered Earth to look at the 3D variations? So one technique we use is called seismic tomography. And so you can compare this a little bit to medical tomography. You send waves inside a body to make an image of what is happening inside the body. And so for the Earth, we do the same. We use lots of different crossing rays, and we try to figure out where material is moving fast or has a fast seismic wave speed and where it has a slow seismic wave speed. Of course, compared to medical tomography, we don't have much control over our sources, assuming we're not putting nuclear, we're not doing nuclear events. And we don't have the ability to cut and check that our interpretation is anywhere correct. Okay? So yeah, this is a big problem. So we pretty much know how we can go from an Earth model to a synthetic data set. We can solve the wave equation. We can do these computer simulations that I showed you videos of at the beginning. But if we have a lot of data and a lot of waves, and we have measured if they propagate, if they've arrived fast or slower than we expect in everywhere on the Earth, then it is a big inverse problem to go from that back to a model. Right? And there's places on Earth where we pretty much have too much data because earthquakes happen in certain places and our seismometers tend to be in certain places, particularly on land, for example. So some places are kind of over-illuminated, and then other places on Earth where we pretty much have no data, and where we can't see any structure. Okay, so our resolution really varies across the planet. So finding a needle in a haystack is hard if the haystack has hundreds of dimensions. Okay? So typically the model that people try to present is what they call the simplest solution, but maybe it's not at all like Earth, right? They try to present the smoothest models with the weakest variations from just a background model. Okay? So the least interpretation they can make that is driven by the data observed. Okay, and so it is a matter of resolution what we can interpret that in this, okay? You're going to see me make hand-wavy things like, ooh, there's a red like blob here, that's got to be something. But obviously, we're not sure, right? And we also don't know if we're missing red blobs in other places, okay? And so actually understanding what is happening, right, might lie in the detail and a much finer scale image of what you're looking at. We also collaborate across different fields to understand this. So one thing is we talk to mineral physicists, and they put the materials that we expect to be on Earth under very high pressure and temperature conditions. Okay? Here's an image of a diamond anvil cell. To reach the kind of pressures that we want, millions of times of the pressure that we have here on their surface from the atmosphere, they need to make very, very small samples so that they can increase the pressure on that very, very small surface area. Okay? Then technically you also want to heat up that sample to have temperatures similar to the Earth. Okay? The center of the Earth is roughly the same temperature as the surface of our sun. So these are very tricky experiments to do to know how the materials might behave at depth. The other problem that we have is that seismology only gives us a snapshot of our present-day Earth, and we're looking at dynamical things happening. Okay? We maybe have a couple decades of data, and our mantle is moving with centimeters per year, so maybe it's moved 1 or 2 meters over the time that we have seismic data. So for us, that's pretty much a static image, given the resolution that we have. So seismology might give us kind of the present-day image of Earth. Back in time, we have a lovely geological record. We can look at the magnetic history on the planet and the fossil record, but we don't have information with depth. So this kind of area in the middle here, deeper Earth, but back in time, relies heavily on computer modelers, building models, like you see on the right here, with plates moving across the surface, and then areas where material goes down and hot material in orange here comes up. And they try to build as realistic possible models guided by what we see as in seismology and guided by what mineral physicists understand how materials behave in the planet. Okay? So it is a very collaborative science to understand what is happening in the planet, and we don't just rely on the images that you are about to see. But our very simplest interpretation of the seismic images is that wherever you're going to see a blue blob, things are moving faster seismic wave velocities, and the simplest explanation is that it's cold. And the simplest dynamic explanation of that is it's cold, it will be denser, it will go down. Whenever you see red, the seismic wave speeds are slower, and that will be a hot, and then we interpret an upwelling material. So seismologists already use this very suggestive color skill that wherever it's fast, we color it blue, and it's cold, and wherever it's slow, we color it red, and it's probably slow, or it is a different composition. Okay, here are some maps that seismologists made. This is at 70 kilometers depth, and I'm showing you 3 different cross-sections. And these have basically been made by 3 different research groups with a very, with some slight differences in the inverse approaches, how they get to model from the data. And they all give like a different acronym to their model that is at the top here. And in the top left, you can see the minimum and the maximum percentage difference from the background average in velocity, okay? So that varies a little bit per model, how strong the variations are. And you can see that one model might be a bit blobbier than the other model, okay? That all has to do with the difference in approaches. But you can hopefully also see that there's some consistent trends across all of these different models. The fastest anomalies represent the kind of cold center of our continents. They represent the bits on Earth that have been around the longest. And the slowest anomalies are along these ridges in the ocean. And this is where the plates are spreading apart and hot mantles coming up and new plates are being formed. And then in the oceans, you have this gradient away from these ridges, which is gradient away with the age of the oceanic plate that is formed. As it's cooling, it's becoming more dense, and the seismic wave speeds are becoming faster. Now we're jumping a couple hundred kilometers down into the mantle. We're like roughly 1/6 down to the core here, 500 kilometers depth. And here you can see the seismic wave speeds are much, much less. Okay, but also our resolution is going down as we go deeper into the planet. Partially because we don't have any surface wave data. This is kind of the edge of what surface waves can see. Can we see some consistency here? Yeah, we have a couple of these broad blue blobs that are in every single picture. And we interpret those as slabs, plates, tectonic plates that have gone down. And some of them have stuck at these depths. Now, the slowest anomalies is a little bit more vague, okay? I should point out to you, these green dots on the map are so-called hotspots. They're places on our planet where we have volcanism at the surface, which is a bit of a mystery. It's happening away from plate boundaries, okay? And so we think this volcanism is called by a hotspot or a mantle plume. So what we expect to potentially see here is hot upwelling material right underneath these spots. And in some places, you might see some weak correlation, but there's certainly not a 1-to-1 ratio with having these hot spots and having a deep mantle plume. Going a bit deeper, we're about 1/3 of our way to the core here, and things get weaker again, and things get a bit more uncertain again. But again, we have a couple places in South America here, next to the trenches here in Indonesia, where we see blue blobs in every single of the model, and there's these elongated places, which we think are previous tectonic plates going down. And again, some blobbiness that maybe correlates with these hotspots, but not very clear, and definitely not clear in each model. Now we're at 2,800 kilometers, and we're just above the core mantle boundary. And actually here we see a bit more heterogeneity again. We see a bit more variation. And we do actually see generally some of the same features across all of these models. We see this ring of fast velocities in all of them, which we interpret to be a slab graveyard. This is where old tectonic plates go to hang out at the core mantle boundary. And we see these 2 broad blobs of red. which we have nicely named Large Low Velocity Provinces, or LLVPs, okay? My field likes acronyms for some reason. Okay, so here are similar tomographic models, so images of the Earth, but now we're cutting through them as a function of depth. And here we're cutting through Japan. Okay? And so here we see then nicely in blue one of these tectonic plates going down. The white dots on here are earthquakes. So you see it correlates nicely where we see deep earthquakes happening on the plate as it's going down. And you can see this plate is getting stuck somewhere in the mantle. This plate is hanging out. So we see potentially different dynamics for different tectonic plates. Because here in Central America, we see a plate that goes deeper, maybe sits stuck there, but in other places, it seems to go straight down and to the core mantle boundary. And we do have a slab graveyard at the core mantle boundary, so we do see that plates end up there eventually, but maybe they get stuck in the mantle temporarily at times. It's one way to interpret these images. Now, plumes going up, or mantle plumes beneath hotspots, have been a bit more questionable. Here is cross-sections through one model, here beneath Cape Verde, St. Helena, Iceland, Canaries. These are all these places where we have this hotspot volcanism happening. And yeah, this model suggests, yeah, there's some continuous feature of a red blob going up beneath these places. Although you would say in some places you kind of lose the image. The plume gets a little bit lost. Maybe it is a broader plume at depth. Maybe it breaks into little plumelets as we go higher up. We don't totally understand this yet. We don't know how well we've resolved these plumes yet. Okay, we tend to do a lot better at imaging the slabs than we do at imaging the plumes. Okay, here is a little video of what these large low-velocity provinces might look like, okay? These are sort of blobs on the core mantle boundary that are thousands of kilometers across and maybe up to 1,000 kilometers high, okay? They're probably very hot. They've probably been sitting on the core mantle boundary for quite a while, heating up. But they might also be compositionally different in ways. Has anyone ever heard of these? Yeah. Not many have heard of an LLVP, okay? Has anyone ever heard of a black hole? Everyone, okay, yes. Much, much better name for a feature, right, than LLVP. You're probably going to forget the acronym by the time you leave this room, okay? Apparently the story goes, by the way, that a black hole got named by an audience member who so it got referred to with a technical term, but an audience member called out that it should be a black hole. So if you find a better name for these features, you're welcome to shout it out. No pressure. It would be nice if we have a better name. In media, sometimes these are called mantle blobs. Okay? In the past, geophysicists have also called them super plumes, which is obviously a cooler name, but it had a little bit too much of an interpretation on it that we're not entirely sure about that they're super plumes, even though they definitely correlate with plume locations, okay? So they have something to do with the plumes. So here is a map of all these green hotspots that I just showed, Hawaii, Galapagos, Iceland, up here, okay? All these places where we have this mysterious volcanism. Actually, this is not all the places, but this is all the places that track to the lower mantle. And you see, for lots of these locations, it correlates very nicely with these LLVPs at the base of the mantle. So they have something to do at hosting. They're kind of the birthplace of these plumes going up. And actually, if you look back in time, we have evidence that there have been super eruptions on the planet, okay? These are these geological features here, the Deccan Traps and Siberian Traps. They're massive evidence of massive eruptions happening in these places over quite a short time scale, okay? Deccan Traps can be linked to happened around the same time as the meteor impact and probably played a role in killing the dinosaurs. And the Siberian Traps might also have played a role at the end of the Permian period, in a mass extinction of life, okay? And when people, these are the locations here in red where we see these features of mass eruptions on the present-day Earth. But here they have been relocated to where we expect they were on Earth, given that the plates move around. And then you can see they correlate quite well with being at the edges of the LLVPs, okay? So we think there might be a good interaction here, well, not a great interaction because it leads to mass extinction, but some interaction between the base of the mantle and the So yeah, a quick summary of the things we see in the tomographic models. We see plates diving down in the mantle. We see mantle plumes rising up and causing volcanism. And we see these two giant mountains of different materials on the core mantle boundary. Let me quickly check the time. Okay, so can we do anything better than that? This is really where my work comes into, okay? So we can try to make these global images of the mantle, but really sometimes it seems like if we can just do a little bit better locally, we can learn a lot more about what is happening in the planet. We don't have to always look at a global scale. So wherever we can get a good geometry of waves, and maybe we can push it to higher frequencies, we can get a better resolution image. And this really relies on having a seismic arrays, so groups of seismic stations standing around on the planet. These maps show you a couple examples of them. And then when we have an array of seismometers, we can really look quite well at the directionality of the data that is coming in, besides the time and everything. And so I've been looking at this particular type of wave a lot over the past couple of years. This is a wave that is diving down to the core, and it diffracts along the core mantle boundary, and it comes up here, okay? I just told you there's a shear wave shadow zone, and no waves arrive beyond this point. I already need to correct myself, I lied. We do get small waves arriving beyond this point in this shadow zone, and they have diffracted along that core mantle boundary, okay? But they're not the direct S wave that we might be expecting, okay? This wave takes about half an hour to go down, propagate along the boundary, and come back up and be observed from an earthquake. Okay, so here's an example of that seismic wave. I'm going to be showing you some wiggles now. Right? This is an earthquake north of New Zealand, and it's observed by seismic stations in southern Africa. Right? And here is, so the waves come down here, roughly at these red points here. They become sensitive to the core mantle boundary. They diffract along it. They come up at these blue points here to be observed at the seismic stations here. In the background is a bit of a weird way to plot tomographic models, so don't worry about it. But mainly, this red blob here is one of these LLVPs, large low velocity provinces. And the blue here is where we think the tectonic plate graveyard is. Okay? Here are the seismic waves, and they're organized as a function of azimuth. And this is the angle from the earthquake to the station. So at the smaller Earth azimuth at the bottom here, we're basically looking at these waves that are propagating in the southern path. And at the top here, we're looking at the waves that are propagating in the northern path, and they go across here, okay? And on the right here, sorry, the labels are left up. The right here is synthetic data. So this is data done with computer simulation. And on the left here is the observed data. You can see the observed is a bit noisier than the synthetic prediction. And what I want you to observe here is that there is this jump in the waves arriving later here and earlier here, okay? And this, I think, is due to that boundary of this large low velocity province, okay? So with data like this, we can see much better how sharp that boundary is, okay? While all these tomographic models give us these very smooth images, here we can see it could be a very sharp, which might indicate there's a compositional variation. It can't just be temperature alone. Actually, at this boundary, you can also see this secondary wave arriving. You can see the wave is splitting into multiple arrivals, and we call this multipathing. We interpret this as one wave is propagating outside of the LVP, one is inside the LVP, and they arrive back at the same station. And so that's really indicating that it's propagating along a quite sharp boundary. Okay, here's a different example where we found something totally new. This is an earthquake in Papua New Guinea, and it's going towards a dense set of hundreds of stations across the US. And here in the purple is where it becomes sensitive to the core mantle boundary, and here is where it comes back up to the station. Hawaii is just over there. This is what we expect in terms of synthetic data. So again, I've organized it here as a function of azimuth. So here from the top, we're going from the north here over to the south here. And there's a couple hundred seismograms in here, but they're plotted on top of each other in small bins with respect to the time that we actually expect them to arrive. Okay? So in the synthetics, you don't see too much. You see a little bit of amplitude change due to the earthquake, and a little bit of a delay due to the background model that we put in this computer simulation. Okay. Now, when you look at the data, we see something entirely different. Okay. And I should note this is higher frequency data than we can incorporate in these tomographic models just due to computation time. Okay. So now, when we go from north to south across this data set, we actually see our wave disappear. And about 30 to 40 seconds later, we see another little wave appear that we don't actually expect there. Right? We call this kind of delayed wave a post-cursor, so I might refer to that as the post-cursor here. Okay, I've highlighted it in red. It has a bit of a travel time move out as a function of wave. Okay, and yeah, we dubbed for very long how we could explain this. And actually, if we put a blob on the core mantle boundary, roughly 900 kilometers across, 20 kilometers thick and 20% slow, okay? Lots of modeling went into that potential model, but it does have this kind of simplified cylindrical shape. If we put the kind of extreme blob of slow velocities on the core mantle boundary in this black area here, we can somewhat reproduce the nature of having this post-cursor with this hyperbolic move-out. And so how do we interpret that? That slow blob is basically causing this focusing, right? It's refracting the wave. We've got this focal point here that it's going through, and it's scattering delaying and scattering this energy around, okay? This is our simplified interpretation of what this blob is doing. And so here you can see that in a wavefront. So here we have a wave coming down to the core mantle boundary. It's hitting this very slow blob, and it's setting up this secondary post-cursory wave that is then eventually coming up and being observed by our seismic stations, okay? We saw we needed something quite extreme to explain this delay time of 30, 40 seconds, okay? And we've been using this type of data to map the core mantle boundary for these anomalous blobs, okay? These extremer blobs, we have another acronym for ultra-low velocity zones, ULVZs, okay? And so these are only tens of kilometers high, which is roughly similar to the thickness of the crust that we're standing on at the surface, okay? So we're mapping something tens of kilometers high, but 3,000 kilometers deep. And they're extremely slow compared to their surroundings, tens of percent slower. And so they cannot be explained by temperature alone. There must be some sort of compositional anomaly, either something that's been iron enriched hanging out, something dense that's been stuck there at the core mantle boundary, or maybe something that is leaking out of the core, okay? Here's a map of all studies of ULVZs. In orange are like, they haven't really mapped the ULVZs, but they say, oh, with our data, roughly in this area, something is happening. There's some heterogeneity there. The dark red are ones that have been mapped in 3D. In a global map. But this is kind of a compilation of all studies that have been mapped interpreting these ULVZs. On the left here, by the way, you see a little cartoon view of a potential ULVZ at the base of a mantle plume, okay? That is a bit of an interpretation because we do find the largest of these features close to Hawaii, Iceland, Galapagos, St. Helena, Samoa, okay? A lot of these have been found close to hotspots. And we see interesting things in the basalts at these hotspots. So these are people looking at the geochemistry of these eruptions in these places, looking at the different isotopes that you can see here. And they're looking at parts per million concentrations of these sorts of features, right? So one thing they look at is helium. And so here in this little cartoon, you can see the helium at these ocean island basalts, I should say, that is at the hotspots, so that's at these mystery volcanic locations, compared to places where a plate is formed, the mid-ocean ridge basalt. Okay? And these values of helium are compared to the atmospheric value, that is Ra. Now, helium, as we understand it, well, helium-3 is a stable isotope over time. Helium-4 is produced by uranium and thorium decay. Okay, so that gets produced over time in Earth. But pretty much any time our material gets recycled along the surface in a plate, our helium gets lost due to decasing. Okay? And so the fact that we see strong variation in this helium feature at the surface, and particularly at these places that have mantle plumes, we see strong enrichment of the helium. And that basically says that it's tapping somewhere in the deep earth a material that is undegassed or has never been across the surface. Okay? So this could be the LLVPs or the ULVZs or material that is stuck at the surface, or it could mean something is leaking out of the core. Okay? The media really got on the core idea of we're very concerned that the core is leaking a mystery element. Well, it's not a mystery element. We know what we think it is leaking. And also, we're not very worried, okay? There's post-Permian signatures that might be leaking across the core mantle boundary. And so if you look at these signatures of helium across all ocean island basalts, we find the most extreme values. Okay, this is all hotspots, and this is helium, okay? I should say there's a lot of bias potentially in the database based on hotspot islands that scientists like to go to and study, okay? But the largest values are in Iceland, Hawaii, Samoa, and Galapagos, what happens to be these places where we see these ultra-low velocity zones. There's another signature. This is a different type of isotope system of tungsten isotopes. So the 182 tungsten is a decay product of hafnium. Hafnium is very short-lived, so it basically gets lost very early on in Earth, and then 182 tungsten gets produced. And 184 tungsten is very stable. Now, hafnium likes to go in rocky bits, and 184 tungsten likes to go in the iron-rich bits. So basically, the hafnium and the tungsten would have split up when the Earth formed its core and the mantle. And yeah, because we see variations in this, and because the hafnium is so short-lived, we know this must have happened very early on in the Earth's history. So on the right here, you can see the summary again in the ocean island basalts or other places where plates get formed. And so if we take these other places as the kind of reference point, okay, the micro here, this is deviations in part per million, then at our ocean island basalts or hotspots, we see this deviation again in this tungsten. Okay? We see this negative deviation. And again, that can be an indication that there's some what we call primordial component in the mantle, something that's been protected in the mantle over a very long time since Earth's early formation, piled up on the core mantle boundary, or it could be, again, a signature of the outer core, which we expect to be very, very negative in this tungsten ratio. Okay? So this is just a map putting together what we see in ultra-low velocity zones and where we see these helium and tungsten isotopes. Okay? Both the ULVZ map here could be biased, as well as the geochemistry could be geographically biased, right? So, yeah, we're not making strong correlations yet, but this is really stuff that's been happening over the past couple of years in both of the fields that's hopefully coming together. And here's work from my PhD student that we are just trying to get published of a global map of trying to use these diffractive waves to consistently with one wave type map where they are. And we actually think there's very few very large ultra-low velocity zones that we can map with this method, which are shown in the red here. And in the purple here, we're actually looking at null observations. We're trying to also make observations. We've been very focused on observations of where these might be, because those are exciting to publish. But we've also been trying to say, like, where are they not in this purple map, okay? And yeah, James and I endlessly go back and forth if we can detect all these signals by AI, right? Because he's by hand gone through over 2 million waveforms to indicate where these types of postcurses might be. Okay, very shortly, the field has now been moving to other planets. Okay, so recently we had a seismometer land on Mars and measure there for about 4 years. One seismometer is really limited in the things you can do. Really even hard to locate where a Marsquake might be. But they still managed to get a lot out of this data on Mars, okay? So they landed actually a seismometer. They also measured the magnetic field. They tried to measure the heat flow, but the heat probe actually got stuck as it was trying to dig down, okay? But the seismometer lasted much longer than they expected, okay? There was a bit of problem with the dust on solar panels at some point, but they had this little arm that had deployed the seismometer that actually picked up some dirt and threw it at the solar panels to try and get the dust to fall down in little avalanches, okay? And this kept the seismometer going a little bit longer. And so they learned also about the atmosphere and dust devils, okay? As somebody who's trying to look into the planet, I often think of the atmosphere as a noise. But in a seismometer, it's very true that one person's noise is the other person's signal. And so, yeah, trying to look into Mars, the dust devils were noisier. But people who wanted to know more about dust devils could map the dust devils and how they were temporally changing through this seismometer. Okay, so they also learned for how Marsquakes work, what depths they kind of happen at. They had a couple impact events, which are very helpful because the satellites can actually locate where the impactor happens. So the data is a bit more usable because we have a good location estimate. And we've been discovering the layers of Mars. The Martian core is proposed in the past year. Potentially an inner core on Mars has been proposed on this data. But we're really stepped back where we were about a century ago on Earth of trying to get that first order layering of a different planet understood, okay? Here's a little simulation of a Marsquake. And the first evidence of the Mars core came from this reflected phase off of the Martian liquid core. Okay, so in conclusion, I hope I've given you a little insight about how we can actually look inside our planet at a scale of thousands of kilometers and say a little bit about the dynamics that are happening in our planet, how our planet is moving about, and how that links to the things that we see at the surface. I've given you a little flavor of the targeted high-frequency types of studies that I work on, where we try to illuminate even smaller structures that we cannot see with this seismic tomography. And the core mantle boundary seems to be dotted with these kind of features. We are currently just tapping into moving on to other planets. And I hope I give you a sense that actually understanding all of these features is very multidisciplinary. We need to work with mineral physicists, geodynamicists, also the geochemists who look at the rocks at the surface to kind of tease all these puzzle pieces together and understand our planet. Thank you for your attention. I'm happy to take any questions.